So what I'm doing here is, you can, for a hash table, you can also iterate through all the key value pairs in the hash table. It's not ordered like an array, but it's still iterable. So what I can do is, I'm mapping through all the key value pairs in the hash map. And so one of them would be, the key would be the number, and so what I'm doing is, so let's say the number I'm looking for here is, an example, like I'm looking for, we'll do 7 again. So if I'm looking for 7, then what I can say is, for all of the hash map entries, I want to say if 7 minus the current value exists in the map, then I return true. And so what that does is, so let's say I'm iterating at 2, then I could do, if 7 minus 2 is in the hash table, basically the complementary entry is in the hash table, then I return true. And basically what that does is, I can say that, so this part here, so basically I can guarantee that I get the right answer every time. But then after you get the answer, your interviewer is most likely to ask you, so what's the runtime of this algorithm? And then you say, okay, so in this beginning part, I'm iterating through my array once, and I'm doing something to it. I'm adding it to the hash table. So this will take O of n time, because I'm iterating through n elements of my array. And then for here, I can say, let's say that the solution doesn't exist, or the solution is the last entry. Then in the worst case, it'll run through all the elements again. And so that's O of n time. But in the end, we know that, so O of n plus O of n is O of 2n. And when you talk about asymptotic runtime, in the long run, it's still O of n. And so that yields a much better solution than a brute force quadratic, which yields a quadratic solution, if that makes any sense. If you have any questions, feel free to ask. Yeah, but so this is probably one of the most basic problems you'll get. And a lot of the questions are about knowing which data structures to use, because some data structures, all data structures have their own trade-offs. So some you can access really quickly, some take longer to access. But generally speaking, hash table is something you should really nail down, because there's O of 1 access and O of 1 writing. So basically, you can do a lot of things in constant time to improve your runtime. Any questions? No? Okay. Did everyone get this? Because basically, in an interview, you're expected to not only get a solution like this, but you need to be able to talk about the runtime complexity, the space complexity, which I'll go over in a bit, and also, yeah, basically, you need to prove correctness, like why you'll get the right answer every single time. Okay. Yeah. So, if no one has any questions, then we can go on to another problem. So last week, I interviewed with Microsoft, and they asked, so a lot of people think that like big companies tend to ask these really difficult, complex questions, but I think what's more important than getting these really niche, difficult problems is like really understand these more basic ones. And so Microsoft asked me last week, it was a pretty simple question. So it's, let's say I have like a string, like race car. Race car is a palindrome because if read back and forth, it's the same word. Basically, given a string, they want to know, can it be rearranged to become a palindrome? For example, let's do, like, if I did ABC and then BCA, this string, while not a palindrome right now, can be rearranged to be a palindrome. And so, yeah. Does anyone have any idea how to solve this problem? Yeah.
If you just count the number of unique characters in the string, and if they, or if it was equal by 2, maybe, it would be a palindrome.
Yeah. So that's a pretty good insight. So basically, if you can split a string up into 2 halves and they look the same on both sides, then yes. So one easy way to do is what's called a mod operator, like check divisibility. And so if I have 2 A's, 2 B's, and 2 C's, then I have a palindrome. You also need to watch for the case where this is still a palindrome. So basically, if I have all even numbers of characters and one odd number of characters, that character can be in the middle and it'll still be a palindrome, if that makes sense. So now we know that we need to iterate through the string and count the frequencies of the characters in it. Does anyone have, basically we need to store this information somehow. Does anyone know what kind of data structure they would use?
Sorry. You can use a hash map again by like, let's say you iterate through and you see R, then you'll say R is your key value, R key, and then your value is like 1. And if you see R again, you'll add 1 to the key R, so now R is equal to.
Yeah, precisely. So one way we can go about this is, so let's say they give you the word as passed in as word. What I can do is in Python, so I can initialize the hash table again here, and basically I'm iterating through. So in Python it's really simple because I can say, for each character in the word, if C already exists in my map. So if I've seen this character before, then I increment its value by 1. And if not, what I can do is I'll set it initialize to 1. And so after this loop, then I'll have the frequencies counted of all my characters. So does anyone want to tell me what the runtime complexity of this for loop is right now? Anyone? Okay. Yes, it is. So because we're iterating, well, it's O(n) with respect to the number of characters in the string. So because we want to know this part right here, this if clause, it's a constant amount of work because we check if it's in the map and we increment it out. These are all things that take a constant amount of time to do, and so we're doing a constant number, a constant work thing n times. Basically, here is. It iterates through the length of the word. And we do a constant number of things. So this overall operation here is O(n) with respect to the length of the word. And so now we have our frequencies counted. Does anyone want to try how we would check if it's palindrome? Now that we have this frequency table? Yeah.
When you iterate through the map and then you check to see if it's a count of 10 characters divisible by 2. You can have like a separate variable to make sure you only have one character that's not repeated from month to month by 2.
Yeah, so basically you can have, for our purposes, we can have at most one character that has an odd number of entries, an odd frequency, and the rest must be even. We can have 0 or 1 odd number of entries. And so what we can do again is, this is the Python syntax. So basically, for each key value pairing, what we're doing is we only need to check the value. So if what this says is it's the modular operator, so check the divisibility. If it's not divisible by 2, what I can do is I can have a Boolean. Basically, this Boolean is like, have we seen an odd frequency before? And so if we haven't, then not odd then. So what I did here is basically you iterate through all the key value pairs and you check for divisibility of 2. If it is odd, so basically if it is not divisible by odd, if it's not divisible by 2, then it's odd. And if odd is currently false, then we know that that's our first odd pair. If odd is already true, then we know that it's our second pair, which means it's not a palindrome, and we can return false. We short circuit it and return false. And then if you break out of this loop, meaning you've gone through all the key value pairs, then you return true. And so for this one, I think the key to note is that optimizing your algorithm is also something interviewers are looking for. So basically, even though this algorithm will run in O(n) time every single time, but something you want to look out for is ways to optimize. It's still O(n) time, but what we're doing here is the moment we see a second odd frequency pair, we short circuit it and we return false. So maybe a more naive solution is you iterate through all the pairs and then at the end you will return false. But what we can do is, let's say all the pairs are odd. We get to the second pair, we see it's odd, and we can return false. And what we can do is, in the best case, this runs for 2 entries, for 2 hash map entries, which is a constant number of times. You can talk about that. Something like that. And so, yeah. So basically, in the top we have O of n time runtime, and the bottom we have O of n again. O of n plus O of n is 2n, but so in terms of asymptotic constants, when you have O of 2n, you want to think about how the coefficient is basically not important as you approach infinity or an asymptotic runtime. And so what you can do is you can argue that your runtime is O of n. And in terms of another thing that they might ask you is the space complexity, or how much space is your algorithm using? And the answer to that is, so we have this this table frequency table over here. In the worst case, let's assume that our string is something like this. Like our string is ABCDEFG. What we do is what our hash table looks like when we're done is it has all these entries with 1 frequency, and so the number of entries is equal to the number of characters in the string. And so in the worst case, the space complexity is also O of n. Basically, what these big O's are talking about is, as I increase the size of my inputs, how does my runtime and how does my space increase? Yeah. And these are both pretty important things that you should be able to talk about after you've implemented a solution. Yeah. Any questions? Okay. So I didn't think we'd get this far. So let me think about a harder problem.
And you might want to make the font bigger.
Yeah, sure. Does anyone have any topics in particular that they'd like to touch on? So, for example, recursion, dynamic programming. I don't know. Does anyone have an interview coming up to prepare for or something like that? Yeah.
Like just analyzing runtime,
Yeah. So, I guess, so to talk about analyzing runtime, the basic way to think about it is, let's say I'm doing like A equals 5, B equals 3, and then C equals A plus B. Basically what all of these primitive operations, so assigning a variable, adding a variable, or doing anything, or doing an addition, it's what you call O of 1. It's one operation, one thing, basically. And so each of these things, A equals 5, O of 1, B equals 3, O of 1. And what we have here is, you can assume this. This is technically, you're adding A and B and then assigning to a variable. It's 2 things. But all that matters is that it's constant. And constants, if you scale it to basically infinity, so let's say we had a loop, let's say we ran this 500 times in the loop. What happens is, what we're doing inside this thing is a constant amount of time. And so it's basically, as you approach infinity, this will always be a constant number of 1. And so that's how you want to think about that. But what gets tricky is, if I have in here, for example, I have a word called hello, and I say what I'm doing here is, better solution. So in this example, I'm going to iterate through all the characters of hello, and I'm going to print them out. In a case where we don't know what the length of word is, we could say, let's say the length of word is length n. And what we do is, for each iteration, we're doing n work because the work of this function is the print function, and so we're doing each print is one thing or one operation. But when you iterate through all the characters of the word, then you can think about it as you're printing n times, and so your total amount of work here is O of n. Makes sense. So runtimes get a lot more tricky when you deal with things like recursion, but just for now, it's important to know, anytime you're iterating through an array, anytime you're iterating through the characters of a string, what you're going to be touching on is O of n, most likely. O of n with regards to the length of the array. So it's important because even if you get the optimal solution for a problem, think about it when you're in an interview. The interviewer isn't marking, did this interviewee get the perfect solution? How long did it take him? That's not what he's marking down. He's marking down, do you have an understanding? First of all, it is important to get the optimal solution, yes, but also, did this person, display that he has an understanding of runtime complexity, space complexity, understanding of when to use data structure and their trade-offs? So a lot more than just, some of you guys might have heard of leak code. A lot better than just going on that site and grinding away at problems. It's to have a fundamental understanding of all these data structures and when to use which. And the hard part is being able to talk about it while you're coding, in an interview. Yeah. I guess we can move to something like a pretty basic dynamic programming question. So have any of you heard of Fibonacci? Or are you guys familiar with the Fibonacci sequence? So let's say I'm an interview and I ask you, so I have a function called Fibonacci, and it takes in a number. And what I want you to return me is, so given a number n, return me the nth Fibonacci number in the sequence. We can assume, I'll assume that the 0th Fibonacci, the first Fibonacci number is 0 and the second is 1. Anyone have any ideas? No? Okay.
Well, is it recursive or is it not recursive?
Yeah. So everyone here is familiar with recursion? No? Yes? Show of hands. Okay, cool. So yeah, there are actually also a lot of problems have multiple solutions, and basically one way to show that you're a stellar candidate is you can weigh the different solutions and why which one's better than the other, or why both of them are optimal kind of trade-offs. So one solution that a lot of people might know is the recursive solution. So the n Fibonacci number is equal to the n minus 1 Fibonacci number plus the n minus 2 Fibonacci number. So something like this. Basically, if I just call, Fibonacci will get me the n Fibonacci number. So if I just call the two previous and I add them together, I should get the right answer. And then so I have base cases like this. So if n is 1, I return 0. And if n is 2, I return 1. Make sense? So this solution is really bad. Does anyone want to talk about why? Does anyone know why, first of all? Yeah.
Basically, you're calling Fibonacci for n minus 2, like n extra whole n times. So it comes to n squared because every time you call n minus 1, you're going to call n minus 1 after that, which is equivalent to calling n minus 2. And basically that follows down, creates a tree, a branching tree this time.
Yeah. So almost completely correct. So the first thing is, what happens here is when you generate, on each function call, what I'm doing is I'm creating 2 more function calls. So you can think about it like a binary tree. It's always expanding. These two, like my original function call creates 2, and it splits into 2. It's constantly growing, right? And the problem with this is, I'm having so many function calls. Actually, the runtime of this algorithm, it's not O of n squared, but it's it's 2 to the n, because think about it. For each function call, I'm growing into 2 more function calls, and one thing you should, I guess, just kind of memorize is that in terms of runtimes, your best is constant time, and then linear time, and then I'm going to skip some, but there's a lot. But basically, you have n to some raised to some power, so some kind of quadratic time. It could be huge. And then beyond that, there is then really bad. It's like this. Then you get to what's called 2 to the n. Actually, so there's a pretty good visual tool for this. So this is one way you want to think about how runtime scales. So as your inputs increase, so you have O of log n and O of 1, constant amount of time at the bottom here, and you see n starts to scale as you increase your inputs a little bit, and then you get to n log n, and then you see n squared at the top, which is it's like pretty much a monster compared to like linear time. this is why, like, for the first problem we did called twosum, you want to avoid quadratic solutions. It's because, you know, if I were to pass in twosum with a million input array, or like a billion or a trillion, then you see like my runtime is going to be much, much slower. So yeah, this is just like a good visual of how you want to think about things. And so you see for 2 to the n, it's even scarier. So basically, you want to avoid this at all costs. Right. If it's the best you can do, then yeah. So actually, you can do a recursive solution, but I think I'll touch on the most simple first. What I do is I can have 2 variables. Let's say I'll have A and I'll have B. What I can do is I can initialize A to 0, B to 1. And what I can do is so the solution I'm going to do here is, it's a lot simpler because basically I have 2 variables, and what I'm doing is I just keep adding one to the other. And I do this n amount of times. So for example, let's say I want the 5th Fibonacci number. What would you do in real life? What you would do is you have the first 2 Fibonacci numbers, then you add them together, they get 1. I have the third one, add them together. So just real quick, I have 0, 1. I have these written down, and then what is the third? I have the previous 2, I have the previous 2, and then I arrive at the answer of 3. So I can basically mimic that inside of a function here. So yeah, sorry, equals 0. Let's see. So we have base cases. So so what I can do is then, yeah, so I'm basically constantly generating the next Fibonacci number by adding the previous 2 together. Yeah, that's fine. And so this loop will run n times. So basically, if I have a loop, from range I n to n minus 2, you can see that the loop runs n times. And as we discussed previously, this inner loop does a constant amount of work. So, yeah.
You don't have to update it.
Yeah, that's what I was thinking about. That's what I was thinking about. So let's do 3 pointers. Plus B, C. Sorry, my brain's like freezing right now. But basically you would add the 2 together. The reason I don't use the solution is because, the reason I'm like tripping on the solution is because it's not the solution I use. But this is what's called an iterative solution. And it's because you're iterating bottom up. Basically, you're using a for loop, and it's iterative because you're iteratively generating the next Fibonacci number. So let's go back to the other solution that we talked about, which is recursive. If we had something like, before we had something like this, and so you might think, we can't use a solution like this because, we're going to generate all these function calls and we're going to end up with 2 to the n runtime, and that's going to be really slow. But you might have learned something called memoization, or basically, what ends up happening when you do this kind of function is, think about every Fibonacci call, no matter what happens, it will end at Fibonacci of 1 or Fibonacci of 2. And what I'm saying is, you have your base cases. So if you have n equals 1, then something like that. So basically, all these function calls I'm generating, they'll end at either 1 or 2. Basically, because to get Fibonacci 5, I call Fibonacci, 3 plus 4. They all these function calls end when they hit basically 0 or 1. These small numbers. So what I can do is, I can say, well, why don't I save? When I calculate the Fibonacci number for a position, I can save the value and I can access it later. So again, I'm just going to use a hash path because it's really fast. So what I can do is let's say I need to calculate, let's say I'm getting Fibonacci of 5, and I need to calculate Fibonacci 3 plus Fibonacci 4. What I can do is, instead of having this return statement, I can check, so I can say, if n is in my map, so which means if n has been calculated before, then I just return the value. And if it's not, then what I can do is do something like this. So what I'm doing is, so in this kind of solution, like it might look like a trivial difference, but I'll talk about later how the runtime is much different. And so what I'm doing is I check to see, my map will store all the Fibonacci values and the nth numbers and what their values are. And what I say is, when I get a Fibonacci call, if I've calculated this value before, then I just return it. And this, the key to this is that this runs in constant time. Because getting from a hash table entry is constant time, it's O of 1 time. But then what I can do is, if I haven't calculated this entry before, then I'm doing the same thing. I'm gonna generate that branch. I'm gonna calculate that number. But when I finish, whatever it returns, instead of just returning it as the answer, I'm gonna store it in a map. And that means that I've calculated it and I can access it for all the future function calls. And yeah, once it's calculated, I just return map event. Yeah. So the precursor to this is, I would say, like, I would start my table entry with 1 is 0 and 2 is 1. So I start with that base cases. And does anyone want to tackle the runtime complexity of this algorithm? Does anyone have any idea? So you see that, like, in the previous picture, we went from O to the n all the way down to O of n. And the reason behind this is because, in a hash table, to get a value, it's constant time. You might say, like, well, we're no longer branching down all these function calls, because if let's say we're asking for 7. The Fibonacci value for 7 gets calculated once. 6 gets calculated once. 5 once. All the way down to 1 gets calculated 1 time. And the difference here is that, once we've calculated something, we save the answer. And that's what's called memoization, and that's something that you might get tested on as well. So essentially, when you do these kinds of problems, try your best to avoid doing repeated work. Anytime you have calculated something before, it's almost always better to save the answer if you need to use it again, rather than recomputing it every single time. If that makes sense. Yeah. And then real quick, so the runtime complexity is going to be O of n, and the space complexity is similarly going to be O of n as well. And that's because you're storing all the from 1 to n the Fibonacci numbers. Yeah. Any questions? No. Yeah.
So it's O of n because, like, when you call, like, let's say you're n is 5. So if you call map with 5,
Yeah.
Because, like, it'll reach, like, the n-1 case and keep doing that for every single element. And then after that, it'll do the n-2, but I saw that, like, it calculated it already because of the n-1.
Yeah.
Or
we can go over, like, a pretty quickly. I won't go use a too big number because it'll get big really quick. But so if we call, Fibonacci of 4, right? This will call Fibonacci of 3. Oh, sorry, Fibonacci of 2 plus Fibonacci of 3, right? And this will call Fibonacci of 1 plus Fibonacci of 2. 1 plus n. 2. So you can see, like, Fibonacci of 2 gets called multiple times. Fibonacci of 1 gets called multiple times. If you increase this number, right, all these Fibonacci numbers are going to get called a bunch of times. And so the way you think about this algorithm is that, so what happens is Fibonacci of 1 and 2 are already stored, right? So we have those answers already. When Fibonacci 1 gets called, what I simply do is, return the map entry. So that's done. We don't do any work there. It's a constant. It's just one access. Fibonacci of 2, same thing. But the first time you see Fibonacci 3 gets called, so in this function call, it'll say, okay, has Fibonacci 3 been calculated before? And the answer is no. So I need to calculate it. So I will go grab the answers here, right? And then when these two return, then I store it here. So In another case, like if we use Fibonacci 5, 6, or a greater number, Fibonacci 3 would get called multiple times after that, and then they would all be constant time because they become just like Fibonacci 2. You just access the hash table entry and you get the answer. If that makes sense.
Yeah. So would you say like a lot of the time memoization problems are O of n time because like you calculate each element once and then you access it?
Yeah, it's usually you don't want to like generalize like oh, memoization is always O of n, because let's say this step here where we calculate it, let's say it was O of n time, then my entire solution would be n squared because you have n entries that take n amount of time. But generally speaking, if you can, so that's how you want to logic it out. You're saying I have n entries to calculate. You know, I have to calculate for Fibonacci 7, I have to calculate 1, 2, 3, 4, 5, 6, 7, right? How much time does it take me to calculate each entry? And the answer is, you know, it's kind of unclear because you're doing something like this. It doesn't come right at you, like it's not like A plus B kind of thing. But you can see that most of your cases will run like this. They will terminate right here. You'll check if it's in the map, it will be in the map, and you return the answer. And this is the key. This is O of 1. And so you have all these constant time function calls. Yeah. Any questions? Yeah.
Yeah. What would you recommend to develop a better intuition for which data structure to use to get optimal solution?
So glad you guys came today. The secret is that it's usually a hash map. That is the biggest thing here. So just because, you know, for a lot of these problems, right, you need to say, a lot of the time you'll say like, oh, is there a 5? Is there a 7? Or is there a number? Or is there a character? And like the problem with an array, so arrays are used a lot more in real life and probably in your classes too. But the problem with arrays is like I can't go to an array and say, like if I scroll up, I can't say, okay, in this array, like is there a 50? Well, I have to iterate through the entire thing, you know, all the characters, all the numbers, you know, all of that. But what I can do is I can say, if it's all stored in a hash table, I can say, does this entry exist in constant time? And that's usually what will speed up your algorithm. Generally speaking, I'm trying to think of times when you use other data structures. So if you guys learned like linked lists, like stacks, queues. So this another secret tip is you never use a linked list pretty much because they're useless. It's pretty much always going to be an array or a hash table. But one way to develop an intuition is just see more problems. Like I think, and it's kind of annoying, but maybe do like a problem a day, or it shouldn't take. Hopefully, it'll take like 10 minutes. You can start with these kind of more simpler ones, and work your way up. But I think the biggest thing is in an interview, like you're going to be more nervous, and you're under a time constraint, usually 45 minutes, and you're going to be on the phone with somebody, and so you need to think about like put yourself in a position where you have to be coding out your solution while talking through your solution, your insight and your intuition to an interviewer in 45 minutes. So what I would recommend is, if you have a friend that is also struggling to do interviews, then what I would do is like you can do like basically you learn a problem and then your friend learns a problem and you go there and like you ask it like you mock interview them basically. And if you really care, some companies what they do is at the end of the final round they have what's called an onsite, and that's even more nerve-wracking because you're in person and it's not a code editor like this. You're writing on like a whiteboard. And so you need to know your language in and out. And yeah, you need to be able to be writing on a whiteboard in correct syntax while explaining your thought process to your interviewer. And know that a lot of the time when you're explaining something, your interviewer might just cut you off and start grilling you. So yeah, you really have to know your stuff. So like a really common thing is like, you might be coding up this solution and be like, oh, I would use a hash table here because yeah, I like a hash table. And they would go, stop. Like, tell me why you would use a hash table. And you have to say, like, well, I can check if something's in there in O of 1 time, and I can also write something to there, so I can add an entry in O of 1 time. And so, like, these are things that you need to know, like, kind of in and out. Because another thing is interviewers are also looking to see if you've just memorized the solution. And if you memorize the solution and they figure that out, your chance is basically 0. Yeah. Any other questions? Yeah.
What's your time capacity when you add an to
So actually, array list is a Java specific thing. But anyway, so the way, real quick, so the way you can think about arrays, the runtime complexity should be the same for every language, or the big O number you should think about. So when you're adding an element to an array, yeah, so this is a little bit more tricky. This is something that an interviewer could ask you as well. You might have learned it in your data structures class, but so yeah, what an array actually is behind the scenes is it'll look something like this. 1, 2, 3, yeah. So what an array looks like is it'll say the size of the array is 3, but 3 of the elements will be populated, but it'll have 3. Basically, it'll have 3 spaces reserved for the next 3 elements. And you guys, you learn that data structures if you pay attention, but I think a lot of people forget, which is why you need to brush up on your data structures. Really important. Because, for example, if you just say I'm using an array, then they might say why. And then you might say, oh, I want to add to an array, and it's constant time. They'll say why. Well, so the answer for this is because they reserve spaces. And so let's say I'm adding some elements, right? So I add 1, I add 1 again, and I add 1 again. Then I want to add something else. Well, my space is full. What happens in an array list? Well, behind the scenes, what happens is they actually copy all of these elements into another array, twice the size of it, and then they just copy all the elements down, and then they have all these new spaces. So this operation, as you guys might know, if you're copying all the elements, this takes event time. Like how would this work? This is really slow. You need to be able to argue for something called amortized runtime, and so what this is this is a very data structures problem, but what happens is, so let's say I have this bigger array, right? Let's say I've got 16 spaces on this total array. My next 8 times I add something, it's constant time. I just slot it in, right? So it's what I do is to add 8 elements, right? I do 8 operations of work. If that makes sense. But then the one time where I need to duplicate everything, I use 8 as well. So the really basic way to think about this is so my one duplication is here, right? So I'm duplicating, and then this is like a general insertion, right? Then so I'm doing 16 components of work, if you can think about it like that. And the total number of elements I'm adding is 8. And so you see that the answer here is 2, or a constant number. So for each add, on average, the runtime is constant, if that makes any sense at all. Basically, so one add will be really expensive because I got to duplicate everything. But for all the others, then they'll be really quick because I just slot something in because I have my slots already open. And yeah, an interviewer might grill you on that. I was asked that pretty often. So beyond so on this website, they show for an array, access, O1, blah, blah, blah. More, don't look at half the bottom half of this. But more importantly is you need to know why access is O of 1, why search is O of n. So for example, if someone asks you oh, why is searching for something in an array O of n? You can say, well, I need to iterate through everything and I need to check if it's there. And yeah, so I would say review your data structures first and foremost, because a lot of the time you might be able to get the best answer, but if they ask you, why is access really fast? Why is access of constant time? Then you need to be able to get a good answer for that as well, or else they'll think that you know how to solve the problem, but you don't have that computer science intuition. If that makes sense. Yeah. Any other questions? Yeah.
Where would you get more than 2 questions?
Yeah, there is a site called leetcode.com. So what I recommend is, oh God. So you sign up here, it's free. So you can go to problems, and basically they have all these sections top, blah, blah, blah. I would highly recommend, so you go to, so each problem here has the name, and then look for the ones with, it doesn't matter if there's a posted solution or not, because people online can submit their solutions and you can read through them. So for example, let's say I want to do do some here. So I click into it, and what's really nice about this site is So I can get like, it tells me the problem. Actually, it's pretty much just like the problem we went over today. And you can code in an editor, and you can select your favorite language here. Just a quick thing, I recommend Python if you guys are willing to learn it. It's a lot simpler. If you're using something like Java, or I don't know if you guys know C or anything like that, but if the harder the syntaxes are, then the more tripped up you'll be during whiteboarding or coding something out. Like you see, like Python is probably the most straightforward. Print, looping, it's pretty simple. So I would use that. But otherwise, so you try the problem here, and you can run your code, which is nice because you can see if the solution works. And if you spend a lot of time on a problem and you can't get the answer, you can either look at the website solution or this discussion page, and you can just sort by the most upvoted post or the most popular post, and they have a bunch of solutions here. But anyway, if you're looking to practice, I would go to problems. I'd highly recommend going to top 100 liked, and just you can sort by acceptance. So usually the question's difficulty is measured by how many submissions get approved versus how many have errors. I would sort by reverse, top down. So I guess the easiest questions first. And you see, like, you don't need to touch, like, if you go to these really difficult problems, right? Like, you don't need to know. Like, a lot of people have this misconception that, like, oh, Facebook or Google will ask all these crazy difficult problems, the hardest problems on the website. That's just not the case. Every interview is a toss-up, but I'd say most of the time they lean towards the medium or easier side, especially for internship positions. So I would work out here, and yeah, make sure if you don't get an answer, if you don't get a solution, then like you read through and understand how it works. If that makes sense. Yeah. Any other questions? Otherwise, yeah. Thanks for coming. If you guys want, you can email me if you have any questions, or if you guys, we can do this again if you guys like this, and you can email me with like questions you guys want to see. Because I didn't know what to do today. So thanks everyone. Oh yeah. Here, just do it.
Can you turn back at NYU?
Oh yeah.
After graduation, internships. So pretty good. So that's gonna get me
It's pretty mad.
So one of your general like
Oh,
my mom knows this guy. He works in the top immigrant.
The only thing
Were you able to figure out the sound problem then?
Yeah.
Oh, awesome.
Hey, Josh. Sounds good. Yeah.
And then
actually there is someone else.
also another one too. Like,
Oh yeah.
somebody's like, yeah, exactly. So another has to go also. I'm just scared to test and never like.
So you need to apply for
I don't know dance.